today from the Department of Psychology, Bioengineering, and the Institute for Cognitive and Brain Health at Northeastern University. And I will talk about user-friendly web apps to facilitate analysis and study planning. So I like to start my talks with, or many of them at least, with this figure, which is a survey of science and medicine by Nature, asking whether they thought there was a reproducibility crisis or at least something of a problem with reproducibility. So I'm actually curious for the people here in the room. I can't see you guys online, sorry, but feel free to raise your hands too if you think that there's something of a reproducibility crisis, full-blown crisis, or some major issues that we should contend with. All right, cool. So that's most of you, and that kind of echoes this survey here. Sort of a majority of people felt like there's at least some major problems with reproducibility that we should be concerned about, even if some people felt like there wasn't necessarily a full-blown crisis, and the word crisis maybe is not the appropriate word to use here. So that was across all of biomedicine, but within neuroscience, we've seen a number of different initiatives to try to improve reproducibility in the work that we do. So there were not just neuroscience, but across biomedical research in the NIH. There were some plans to improve reproducibility in their funded work. If you've had to write a grant recently, you might have had to write a rigor and reproducibility section. That's kind of a newer initiative from the NIH. In Amgen, oh yeah, the slides are gone. That's that. Goodbye slides. Yeah, so Amgen talked about raising standards for their own preclinical research. So that's a major drug company. And then here in neuroscience as well, we've talked about major issues with power across different fields in neuroscience. We've talked a lot about problems in neuroimaging as well, some of which you've heard already here. And one common theme that people have come back to as one solution to this problem is to use more precise analytical methods. So there are a number of different ways we can address reproducibility, but this is just one way that many people have converged on. So I'm going to talk about how we can get towards more accurate methods, more accurate inferences, really. And there are a couple different things that are considered the cornerstone of accurate measurements from kind of a more formal measurement theory perspective, and that's reliability and validity. So reliability, yeah, you guys won't see this, but reliability generally refers to the ability to get similar results given repeated trials. And validity refers to some correspondence with some desired outcome. Are people out here seeing the animations all right? Yep, okay, perfect. Because we are about to have an animation. So this is just one example of some of these concepts. So if we have this target and our desired outcome is to hit the bullseye in this target, and we shoot in this way, we can see that the arrows are clustered pretty closely together. So this is a pretty reliable shot. We tend to get similar results given repeated trials. But you can see that all of these arrows cluster away from the bullseye. So it doesn't have full validity in the sense of actually lining up with our desired outcome. If instead we shot in this sort of pattern, so you can see that the arrows are much more spread out one from the other, that means that we're a bit less of a reliable shot because there's a lot more variance in each individual trial. But in this case, if we took kind of the Euclidean mean of all of these different arrows, you would see that it does converge upon the bullseye. If we kept shooting in exactly this sort of pattern, you would see that maybe it is, if you took the mean of everything over thousands of trials, maybe it would converge perfectly upon the bullseye, or like almost perfectly. So in that sense, we have kind of validity on average across many repeated trials. So the underlying process that describes our ability to shoot the arrows is valid, but it's not as reliable. So you could see why we might want both validity and reliability. If we have something that's perfectly valid, but each time we shoot the arrow or each time we run an experiment, it gives us a really different result, that's not very useful unless you're willing to do thousands of those experiments. If the reverse is true, if you have a very reliable experiment and you always get the same result, but it actually doesn't converge upon the truth, that's not very useful either. So if you want to learn a little bit more about reliability, we have a number of different publications, and one that I point you towards is sort of a bigger picture guide to the measurement and interpretation of test-retest reliability in fMRI. And I'm just pointing out that there's a PhD student in my lab that's investigating some of these issues from a subcortical perspective. But we're going to focus mainly on validity today and some of the tools that I'll talk about. And again, validity, we're looking for correspondence with a desired outcome. And typically, I'm going to be talking about validity of our inferential methods with the standard goal of limiting false positives and finding true positives. So let's talk a little bit more about that. So there's a lot of discussion about how to improve power, our ability to detect true positives in fMRI. And part of that is built into this discussion of how to get more reproducible results. If we can detect things that are true more often, then we'll get more reproducible results of finding that true thing. And there have been a number of papers that suggest various ways to improve power. So maybe better sample sizes or more reliable. Oh, I think someone might have sound on. Okay, great. Thank you for turning that on. So better sample sizes, more reliable measures, more powerful study designs, inferential procedures, etc. But along with these suggestions have raised other questions. You know, better sample size would be great. How large do we actually need these sample sizes to be? Some people have suggested that in some cases we might need consortia level sample sizes. Is that correct? How big of a consortia? We might need more reliable and valid measures, but how can we tell which sort of measures are more reliable or more valid than others? What sort of methods do we have to measure that? Maybe better inferential procedures, but which ones are really the best? And so on. And answering these questions requires us to be able to estimate power specifically in the context of neuroimaging, which is a deceptively difficult problem. So I'm going to talk about a path towards better estimation of effect sizes and power to help aid us all in better study planning. So the first step is to understand what sort of effect sizes you might expect for typical study designs. So this is part of why it's so difficult to do these sorts of things, is that often we might not have a good idea in mind of what sort of effect sizes we might expect for a study, or else you would have already done that study. And often you might need larger sample sizes to estimate these effects with great precision. I think I'm getting another echo here. Okay, thank you. All right, so often we don't have the sort of effect size maps that we would need to do very accurate study planning. And then a second step, after understanding what sort of range of typical effects we might expect, is to develop a power estimation algorithm that's tailored for the inferential procedures that we use, the sort of data and studies that we might be interested in specifically, which is also difficult. And I'll talk about that more in a bit. But we're going to start by understanding what sort of effect sizes we might expect in typical studies. So this is the first of the two web apps that I'm going to talk about today. So I'll start by talking about how we might define typical studies. And here I'm going to refer to a study as any sort of analysis designed to estimate the effect of a unique phenomenon in a given data set. And so I start with 7 different data sets. We all start with 7 different data sets that reflect 5 different sample sizes. So the main criteria in starting this study was to look for large publicly available data sets. We've kind of informally chosen this word large to reflect greater than 500 subjects in some previous work that I've done. Now we're going to make that a little more lenient and allow there to be 400 subjects to allow us to include more studies, more big studies of an order that we haven't seen before. We also included a specifically clinical data set that's smaller, only on the order of 100 subjects, but in order to have explicitly clinical samples rather than sort of clinical adjacent samples. And then we estimated 2 different types of brain mapping modalities, both activation maps and functional connectivity. And we're also looking at 3 different types of effects: t-tests, 2-sample t-tests, and correlations. And then 6 different outcome categories. So different types of psychological categories, cognition and psychiatric outcomes, and different types of more physical, quote unquote, categories, biometrics, age, sex, with, of course, the caveat that sex is both a social construct in addition to having some physical characteristics that are measured. And they're measured slightly different ways across different types of data sets. So in total, across all these data sets, sample sizes, mapping types, effect types, and outcome categories, we have 63 different unique studies. that we're going to look at and create 63 different effect maps from that. For this study, we actually convert all effect sizes to Cohen's d. We also convert them to R-squared, which I'm not going to present here. We also do a few different things to them, control for different types of motion, which I also want to talk about right now. But I just want to say that for Cohen's d, this is just kind of a starting place for comparison and interpretation of effect size across different study types. Noting, of course, that Cohen's d has different implications for both within and between sample Cohen's d's. So the same exact Cohen's d will require different numbers of samples to achieve 80% power if you have a d for a within subject test versus a between subject test. So just sort of keep some of these things in mind. There are some limitations to be able to directly compare effect sizes across different types of study types. But it's just kind of a starting place to help us contextualize the effects that we measure within the results that have already been observed in the field. All right, so in addition to measuring things with Cohen's d, another thing that I'd like to point out is that we're using not just normal confidence intervals, but simultaneous confidence intervals across all edges or voxels. So as a reminder, for a confidence interval, let's say a 95% confidence interval, you would expect that in 95% of all experiments you could possibly do, so out of infinite experiments, you would see the true effect somewhere in that interval, 95% of the time. It doesn't really say for a single experiment, we're 95% likely to observe an effect there. It has to do with how often you would see an effect across infinite repetitions of an experiment. So likewise, for the simultaneous confidence interval, this is kind of like a Bonferroni correction for confidence intervals. It helps us control the rate of having errors across all edges within a study or all voxels within a study simultaneously. So if we have, thousands, tens of thousands of edges, we are going to see that those confidence intervals uncorrected will have a higher rate of error just by chance of controlling the probability of seeing the correct effect within all those confidence intervals. So we want to widen it so we're really sure that for a single study, 95% of the time, all of the effects would be within those intervals. Anyways, that's one kind of caveat that I wanted to mention here, but we can go more into that if people have questions. So I'll show a few representative studies from the Human Connectome Project. So for between subject study, what people might often call a brain-wide association study, we're going to look at the correlations. That is, when we do correlational analyses with, let's say, usually edges in a connectome, we often call that a brain-wide association study. For one of these representative studies that I'm showing here, all of the confidence intervals overlap with 0, which suggests that, the true effects could be anywhere in these confidence intervals, but it also could be 0. So all these edges could be trivially small. For a 2-sample t-test, which we might refer to more as a group contrast, and in this case, we have 2-sample t-tests for a number of different things, but here I'm showing biological females compared to biological males. We see that 80% of those effects could be 0. They overlap with, 0. For a 1-sample t-test, here we only have, for the 1-sample t-test, task versus rest. Either task-based activation, which is intrinsically kind of akin to a task versus rest, or task connectivity versus rest connectivity. And here we see that about 30% of effects could overlap with 0. So we have more kind of non-zero effects. And then for activation, again, we have a task-based activation, and it's similar in spirit to the functional connectivity contrast that I'm showing above. We also see that many effects could be 0, but maybe a few more could be non-zero. So in summary, just looking at the conservative effects, so the smallest possible effect we could think might be possible for these studies, we can see that the task-based activation studies or task-based contrast studies, so these studies that really have a within subject design that's happening in the scanner, we tend to observe more non-zero effects and larger effects for those non-zero effects than we observe for group contrast studies or brain-wide association studies, which are more between subject kinds of phenomena. And we can look at how these results generalize across a number of different studies. This is just a subset of all the studies that we have in the database. that I'm showing here, but just to give you a sense that we tend to see kind of a similar pattern across different studies within the same category. We have now kind of also done this analysis between different types of outcome categories as well. We tend to see that associations with psychological phenomena tend to have smaller effects or effects that are difficult to distinguish from zero, compared to studies that study more physical kind of properties. So that's just another way of sort of thinking about this, but you can think back to the figures I showed previously. They tend to generalize across different types of studies. So something I like to think about is to be most conservative. It might help to plan for most effects to look like this. For between subject studies, it's possible effects could be very, very small. Most effects could actually be very close to zero. We just don't know with the current precision of our studies, given the largest possible data sets that we have access to. Yeah, JB.
Just quick question on the independence of all those states versus non-independence. Like, it sounds to me like if they're not independent, if you have a kind of a point giants, the confidence interval, let's see in terms of that non-independent aspect.
That's an excellent question. So there's definitely strong dependence across the connectome and across the like task-based activation maps. There isn't a very clear literature that I've seen to construct these corrected confidence intervals to specifically account for this dependence, or at least a literature that sort of has landed on you should do it this way versus this way. But to sort of account for some of that dependence, we also estimate effects at the level of networks. So pooling within networks where we expect there to be dependence. And then we also estimate effects at the level of, we also estimate multivariate effects, so both canonical correlations and Hotelling t-test, Hotelling t-squared statistics, which I'm not showing today, but the results are in the effect size Explorer web app that I'm going to show in a bit. And that's a great question. I'll say I wish I had included it here, but we tend to see larger effects with network level effects and also with multivariate types of stuff. For the multivariate stuff, first we do dimensionality reduction, and then we estimate the effect sizes. I think reducing to something like 30 subjects per variable, which has been shown by Helmer and colleagues to yield really high stability in the estimated effect sizes. So just to say it's not like 30,000 dimensional multivariate effect. But anyways, yes, you tend to get larger effects when you use network level and multivariate types of tests. And since we're not expecting people to have, thousands of subjects on hand the way we have in these kind of big studies, it seems like it could be a really good starting place for people to start with these sort of larger scale inferences and then drill down, kind of like an omnibus test. Start with maybe a multivariate test, and then maybe go to a network level test, and then maybe go to finer scale inference, just embracing the fact that you might not have the power to detect such spatially refined effects. So thank you, it's a great question. All right, so at the univariate level, you might expect, at least from kind of a conservative perspective, the most cautious approach you could take is to plan for these effects to be very, very small. Our maximum conservative effect size across all these studies is less than a medium Cohen's d of 0.5. For within subject types of analyses, so task contrasts within scanner, we can see more kind of modest to medium effect sizes. There's a substantial number of non-zero effects. Our maximum conservative Cohen's d across all of these studies is greater than a large Cohen's d of 0.8. So, that's pretty big, but you would also have to be very lucky to be looking at that one particular part of the brain out of all hundreds of thousands of variables. So take that also with a grain of salt. We tend to do these like more data-driven multiple testing approaches where we look across the whole brain. And this is a quick table. It's a little bit out of date now with all the new studies, but to detect the maximum conservative Cohen's d, for the maximum conservative Cohen's d for each category, which is what I started to hint at above, you would need about 400 subjects for a correlation, 68 subjects per group for a 2-sample t-test. Actually, for the correlation, it will be about 800 subjects, because we convert that correlations to a D, which is akin to like a group contrast. So about 800 subjects to detect a correlation, about like 140 subjects to detect a two-sample t-test, 4 subjects to detect our biggest effect in the task contrast functional connectome, and 5 subjects to detect the biggest effect in the task-based activation study. So you can see, of course, we have much bigger power to detect these really big effects for the task-based contrast kind of cases, and less power to detect them for the between subject cases. But if you got lucky and saw the really biggest effect, you could detect some of them with, let's say, 90% power for the two-sample t-test, but 30% power for the correlation. So this is kind of a big overview of the sort of effect maps that we've been estimating, and the sort of the findings that you can extract from looking at these big effect maps from the largest data sets that we currently have access to. But we've also developed a Shiny app for digging deeper into some of these effects. So I've been kind of glossing over results within certain categories, within specifically statistic type categories. But you might be interested in a really specific kind of study or a specific kind of outcome category. So we've developed this app to let you explore that further. So I would point up here and say, feel free to scan this QR code, but on your computers, feel free to scan the QR code if you want to check out this app. I wouldn't all go there all at once, or else we'll probably crash our server. But please feel free to check that out at some point. Let's see if we can go over some of the highlights. And I have Hallie's picture on here. I meant to point out Hallie has developed a paper describing this. She's been leading the initiative of actually developing this web app. She's awesome. She's an incoming PhD student in the lab. So thank you, Hallie, for that. And a little bit of an overview of brain effects. You can, on the left side, you have a bunch of drop-down filters that let you filter different types of data sets or test types or what have you. You can also, once you choose those filters, you'll be able to visualize which exact types of studies fall within that categories that you filtered. And you can also visualize the point estimates, not anything about the confidence intervals, but just the point estimates of those effect sizes. Note that the point estimates are, when you have 30,000 variables, they can be a bit misleading, especially when you have really small studies and you have so many variables. The estimates on the very ends will be really, really big, just necessarily. So I like to look at the conservative estimates, and I'll write more about that in an upcoming paper. Yeah, but we have those point estimates visualized, and we also have activation maps visualized. But in addition to all this, if you don't want to just point and click and look, you can also download the data. We have a download data button, and you can look at all the effect size estimates. You can look at, we've corrected for statistical control of frame-wise displacement for motion, and we've done thresholding by motion separately. And we have all the multivariate network level stuff, and we have the R-squareds and the Cohen's d. So if you need effect sizes for some reason, please feel free to check that out and download some data or explore it visually.
This QR code doesn't work, by the way.
Oh, the QR code doesn't work? Oh, I'm sorry. Maybe it's died. If that's the case, maybe is it? Appreciate it. Ariel just put a link in the Slack. Thanks for bringing that up. All right. Yes, and you can download. We will not walk through an example right now in the interest of time, but I will say we also created a contributions pipeline. So we're looking for hopefully data sets with more than 500 subjects. If you see a data set that's not listed here, we would love to work with you to bring your data into brain effects. And so filter, visualize, download, and contribute. Contribute is now underway. Check out the paper for more details about contribution, and feel free to reach out to me or Hallie. So a little bit about the architecture. So we have the subject level input data being ingested via MATLAB and doing group level analysis in MATLAB. We chose to do that because most of our collaborators are using MATLAB, and I think most of the field tends to still have outcomes in MATLAB, or they often construct, especially connectome outputs in MATLAB. That might be changing, but at the time of creating this project, that was true for us. So we have a contributed data format. So if you do want to contribute data, we've come up with this structure. So you have an overall MATLAB file that is a structure, and it contains information about your brain data, some information about your study info, and about the outcome variable that you're working with. And we walk you through exactly how to fill this out. And if you're unsure, you can leave out information, but you can always work with us to fill that in. Otherwise, we will reach out to fill that in on your behalf. And the way that this data format is set up, it allows us to automatically run the appropriate test, either a correlation or a 2-sample t-test or 1-sample t-test, without you needing to tell us exactly how to do it and how to format stuff. So that's that data format. As an aside, I think JB, we were talking last year about like contributed formats for statistical maps. And this is kind of one starting place for like what that contributed format could look like. But we're super interested in talking to people about other formats. All right, so that first part is doing the group level statistical analysis. And then the second part, we move to R, which is better suited for a lot of different types of statistical analysis. It's what its whole life purpose is. And we use R for effect size estimation, and also for this R Shiny web app, which lets you really easily convert things from some data that you're visualizing in R to a point and click app. So recommended for people if you're interested in building web apps and you're dabbling with R or interested in R. It's a really, really nice platform for translating what you do to something that people can actually use. Yeah, so it's hosted currently on Shiny Apps. Our overall structure looks like this. We have an app with a UI and a server component, and then we have some data component behind that that gets read in, and some helper scripts. And now we have a separate package an R package that helps manage the plotting and all the different types of statistical organization. All right. So that's a lot about effect sizes. That's a lot about sort of our best guess of what effect sizes might look like using some of the largest possible data sets that we have access to. And that's step one, understanding what typical effect sizes might look like. Step two is developing a power calculator that uses these effect sizes that are tailored to the sort of analyses we do in fMRI, so that everyone in the room and everyone abroad can have a starting place for doing a power analysis for your own studies. So there are some existing power analysis methods that exist in neuroimaging. I'll say a few of them. Oh, right. So there are a few different shortcomings of them. I think one of the big shortcomings is, even though they're all like a really nice start, many of them are not actively maintained anymore, and some you can't reach anymore. So when people ask me, oh, how should I do a power analysis? Usually I'd be like, there's not a really great strategy right now, but you can start here. Now it's kind of hard to start there. And that is unfortunately a bit of a reality. Sometimes methods development doesn't get the sort of support that it deserves to have long longevity. But another, some limitations that are worth mentioning are that some of them rely on sort of parametric procedures. So you use equations to be able to estimate what error rates might look like. But a lot of procedures that we're using now in neuroimaging that are suggested to use are non-parametric. And so we don't have equations to estimate what error rates might look like. So it doesn't work for non-parametric procedures, or sometimes kind of arbitrarily complex procedures where you make a lot of assumptions. So that's one issue. And another is that often you're required to bring your own effect size estimates to these power calculators. And as I said before, it can be really hard for people to get accurate effect size estimates. I think the days of running a study with 5 subjects to try to plan what sort of power you might need, I think people are moving towards an expectation that we might need a more sophisticated approach. Like I showed you those error bars, if you can imagine with 5 subjects, you might estimate an effect size that's 0.8, and the real effect size could actually be negative 0.3. So, it's worth sort of considering these caveats with sort of traditional power estimation. So those are a couple shortcomings. So there's a new approach that we're developing in the lab, which relies on empirical benchmarking. So it's kind of a resampling based approach that I can go into more later in the interest of time. But it allows you to estimate power for kind of arbitrarily complex inferential procedures in a non-parametric way. So we are looking at power for multiple different types of procedures that are commonly used in neuroimaging. And Fabrizio Cravo, who's online right now, is leading the very hard initiative to make such a power calculator that is fast and efficient and is flexible to different types of data and different types of inferential procedures, and brings in C++ routines and stuff like that. So thank you, Fabrizio. I think he has a paper that is mostly finished. Bravo. Yeah, so we're working on that. Pros, users don't have to define the effects. It's adaptable to arbitrarily complex procedures. It's easy to use because it'll be a point-and-click web app. The cons are that we're really limited to the generalizability of the studies that exist in our current database. But with more user contributions, hopefully we can make that more generalizable. And at least I think of this as a good starting place in lieu of not having information, and having ad hoc procedures to plan your studies. All right. So in summary about brain effects, plan for considerably small effects. We tend to see larger effects with physical outcomes. Also, for large publicly, it's really nice to be able to use large publicly available data and empirical benchmarking to provide practical guidelines. This is something I don't think we take it for granted now per se, but it's something that really wasn't possible even a decade ago. So, it's amazing that we have all these data sets to find a starting place and practical consequences where we can evaluate where we might need consortium level studies or where you don't. And as I was sort of alluding to, this also points to a need for a more broader scale approach. I didn't get into all the philosophical reasons as to why we might also prefer such an approach, but at least pragmatically, we tend to have better power at the sort of sample sizes that most people are using. And part of that is because effects do tend to match this sort of broader scale perspective. All right, so check out the app whose QR code totally doesn't work, and stay tuned for contributions. Now we're going to move on to the next web app, which is independent of the effect size power calculator study. So let's say you did a power analysis and you collected some data, then it's time to analyze your data. And here I'm going to introduce a web suite that is led by Dustin Shinos and Xenophon Papadimitris that I've been lucky to be part of, that I think is really, really cool. So an overview of this web suite called BISWeb is that it's fully web-based. It's really easy to use, again, but it's very, very powerful. It does, a lot of things that you might expect something like AFNI or FSL to do. You don't have to install a thing. It runs across browsers. No servers are involved. All processing is done locally. And then it involves a lot of really interesting novel architectural elements and features that are introduced by Dustin and Xenios. So there's an intro video here. Maybe I'll run it. All right. I'm just going to run this intro video. So give me a sec, guys. That link works. All right, and hopefully you can hear. Move this.
Bioimage suite. Bioimage suite consists of a collection.
Oh, yes, I probably am. Thank you. All right. All right, we're going to stop sharing and we are going to share. Hi, everyone online. Bioimage suite. Thank you. All right, open it up. And let me know if you guys have difficulty hearing.
Welcome to Bioimage Suite. Bioimage Suite consists of a collection of applications which is likely to grow over time. The list can be accessed under the Applications menu in the upper left side of the page. The orthogonal viewer shows a 3-orientation view of images as well as an overlay. Several image processing and segmentation tools are available to alter images. The connectivity viewer will load matrices from parcellations and show a 2D semicircle representation of a 3D brain view of the edges and nodes. The MNI to TAL is an application map to load MNI to TALRAC coordinates and vice versa. You can drag the mouse to certain brain areas, show the Brodmann areas, enter coordinates by hand, or choose the Brodmann area to view. The image editor is an application that can be used for interactive segmentation and VOI analysis of images. The overlay viewer is an application optimized for displaying functional overlays in the 3-slice orientation view or mosaic tiled view of one orientation. The user can manipulate the threshold and cluster values in either view. The dual viewer tool is an advanced viewer application intended for image registration tasks. In one of the applications, you can click on the brain in the upper left and return to the original page. Under the Downloads tab, you can download a desktop version of the software if you prefer it, as well as a link to the Legacy Bioimage Suite webpage. The Documentation tab includes the user manual, a presentation about how the applications were coded, as well as the developer documentation.
All right, cool. Let's go back. Oh, and I want to get rid of this. Hide the meeting controls. Excellent. Okay. Yeah, so hopefully that sort of illustrated some of its uses and how easy it is to use. So I'm going to dig in a little bit to some of those panels. Starting with the overlay viewer, I like to start with this one because this is something that everyone can use for figure planning, or if you just want to look at an image really quickly and you don't, let's say you're working on a different laptop that doesn't have FSLIs installed or something else, you can just drag your nifty image to this viewer and you can start looking at things. So we typically could have a tutorial for this one, and people are able to go to the website for this one. It can handle more traffic, so feel free to do that. I know in the interest of time, I might not go through it in as much depth as I usually would, but feel free to try some of these directions out. So if you open the overlay viewer, you could drag and drop your nifty image. You can just imagine me drag and drop an image, and you can also load in an overlay. You can also just click help load sample data, and then you can play with some of the viewer controls. Actually, I think I will just show this one and I won't go into as much detail with some of the other ones. So give me a sec. Yeah, all right. So I'm going to Bioimage Suite, opening the link. I'm stopping sharing here. We're going to go back over to Bioimage Suite. All right, so here we are. And we're going to the overlay viewer, which is here. And so here, I'm just going to load some sample data. And you can see how there's, a standard MNI T1 underlaid and some sort of statistical map overlaid. I could, get rid of some of the labels if I wanted to make this a figure. Again, getting rid of some of the labels, I could increase the number of columns or rows, a couple rows. And I've used this to make a number of my own figures in the past as well. I make the increments smaller, make the first slice smaller, change the number of increments, maybe 8 increments, make the first slice way at the bottom. Yeah, but you can play around with this and look at different views really quickly and easily. If I had a nifty image on my desktop here, I could just drag and drop it. Let's see, is there anything else we want to play with? Yeah, oh, you can change some of the colors. Here, the overlay colors are what you might care more about. There are a few different presets. It's object map if you have a categorical, or rather like just integer kinds of values. That's a bit intense. You can change the minimum of the overlay, maximum. Yeah, so that's just one example of how I'm quickly and easily doing a bunch of image visualization stuff in my browser. And really, if I had data, it would really live on my computer. All right, so that's kind of the overlay viewer. Now we're going to go back. All right, let's get this. All right, so that's, again, the overlay viewer. Something that's really cool about this is that you can make something called a live figure, which saves the full application state alongside your data. So if you've loaded some data and you have all these thresholds and all these like colors that you've chosen, and you have specific slices that you want to visualize, and then you want to show your PI, oh, does this visualization look good? Or would you prefer different slices? You can actually just download something called a live figure, and you can email them the live figure. And they just open BISWeb and they drag and drop that file, and they'll see exactly what you saw. And then they can say, no, you know, I want this color instead, or I'd prefer to show these slices, these exact slices, which is really a nice way to collaborate with other people. If your PI is in Hawaii, they can open it up on whatever computer anyone has at hand and look at this stuff. And you guys can just actively collaborate back and forth. So yes, lets you continue where you left off yourself. If you're in the middle of something, lets you share your work with other people. You can also include a live figure in a publication, let's say as a file. And then whoever's reading that publication could then go back and look through the live figure and see other views that you didn't select, and dynamically change stuff. And here's some directions. So previously we did the stuff on the overlay app, and then the second step would just file, save application state. And then if you want to load it, you then do file, load application state, or you can just drag and drop the live figure. So feel free to try a live figure from the cluster failure, power failure paper, which I've included down here, either now or at a later date. All right, so that's live figures. There's also a cluster reporter. This kind of gives you some statistics about all the clusters that you got from your image. On the left here, the coordinates and the size and like how strong the effect was at the peak. Here's some directions for being able to play with clusters. You can click different peaks and stuff and save it as a table. All right, there's also an orthogonal viewer, which is pretty similar to the overlay viewer, but it has more engineering kind of functionality. So you can do some image smoothing, you could combine images, you can do some other stuff too. Again, all here in your browser, following some of these instructions down here. So if you really quickly wanted to take a difference between, let's say, an image that you were registering and the reference image, you could just load them both into the viewer and click difference, and then you'd see all those differences. All right, yep, and that's that tab, image processing. You can correct bias fields to segment images, deface. We include a little defacer based on MNI, registration to MNI Atlas. Yes, and we have a defacer to that too. And again, defacing you're usually trying to do to anonymize your data. And as such, you wouldn't want your data to be like transferred to some server somewhere. And this is all happening locally on your computer. It's just like the browser's an interface. So it's safe in that way. We don't touch your data. Nobody else touches your data. There's also a dual viewer tool. Some of our colleagues who work with rodents have been using this one, but we can also do things like registration here. Let's see. Yes, but I don't have directions for this. This is a nice proof of concept because registration is often, especially nonlinear registration, is one of the more time-consuming steps. And the fact that we can do it almost at speed in the browser is pretty neat. And then we have a connectivity viewer. This is one that I think most people are using from the Bioimage suite of tools. You can create circle plots, you can create 3D plots, you can inflate the brain surfaces more or less. The one limitation right now that we were working on when I was in my PhD a while back was allowing people to upload different types of atlases. We have that in a beta version, so look around for that, but it is not fully tested. So keep that in mind. If you're using the Shen Atlas, that's great. Or if you can transfer your data to a Shen Atlas. Feel free to follow along the instructions in the app at a later time. So there are some sample matrices you can load if you go under help, and then you can play around with different viewer controls. You can make chord plots or these line plots. You can make summary matrices, and then you can save everything in a nice format for publication. All right. One thing I'd like to highlight here that Xenios and Dustin were really passionate about from the beginning of this project is the creation of regression tests. for making sure that they didn't break anything whenever they uploaded or whenever they created a new version of the software, and not just necessarily explicitly break the software, but maybe introduce small unintended changes. So you can biopsy BISWeb if you wanted to, change it in some way. This is maybe in a little bit more depth for than we need to go into right now, but please feel free to ask some questions about this if people would like more details. But I'll say at a very high level, there are tests available for checking that nothing has changed with the display, that nothing has changed with the specific modules like smoothing algorithms. And you can also just choose any module that you'd like to test. And there are a few different ways to test these things. But the most common way to test it is to just go under the, developer info, run display regression tests, or run whichever regression tests in here. And you see, the visualization pop up and it shows you the old visualization and it says whether there's a difference. All right, and then a quick note about architecture. So I think the most noteworthy thing about this web app is that it's built in, all the low-level processing is built in C++, but then it's compiled mainly to WebAssembly, which allows us to both use C++ code in the browser and compared to native C++ implementation, we achieve let's say if you use JavaScript, you might see about 50% of the speed that you would have with C++. But with WebAssembly, you have about 90% of the speed. So we get almost as fast processing, but now you have a web app rather than a more complex software, complex from the user perspective. There are some JavaScript layers that let us do some things. You don't have to install anything. That's the big thing from the user perspective. There's no servers involved. And we also can make use of MATLAB commands and Python commands. Compile that to WebAssembly too. All right, so an example that Merave used, Merave Salehi in 2018 was you could call this individualized parcellation module from JavaScript. You could call it from Python, or you could call it from MATLAB. And you can see everything is using this library, this similar individualized parcellation library. So this is one kind of example of how one might use it. And then we've shown all the web stuff. There's also command line tools for this. I'm not remembering the exact details from back then, but there is a somewhat streamlined process to convert from the web app to, I think, using Node to these command line tools. But if anybody is interested in that process of converting from, web app toolkit to command line toolkit, feel free to reach out and I can put you in touch with the main developers. But you can then, instead of, doing the smooth image in the browser, you install it really simply using npm install bisweb node version. And then you can just do, bisweb node smooth image and then specify your image smoothing parameters, or run the regression tests. This is another way you can run the regression tests. All right, and there's the package. Should be a working QR code to the package for npm. All right, so that's a lot about this second project. It's sort of a really big like bioimaging full suite of tools that is aimed to be available on the web. There's hope that we would integrate more statistical capabilities in here as well, like doing group level analysis. We had been working with AFNI for a bit on some of this, but at this point, there's been, the world around us has been really interesting, and things that we would like to get done are not progressing. But I think what we have in terms of this app is just so cool. I would love if anyone is interested in contributing to a project like this or would like to take any part of it. I know Dustin and Xenius are also really just excited philosophically about the backbones of this project and how it could help make different types of tools more accessible to people. All right, so with that said, I've talked about a lot of different tools. Effect Size Explorer, Power Calculator, there's CSF correction stuff that's happening in the lab. There's network-based inferences. If you want to do ICCs with multiple factors, that might not mean anything in the context of what I talked about today, but if you do care about such a thing, we have a tool for you. And then BISWeb. And I'd like to thank many, many people who were involved in making all of this and related projects happen. So at this point, I will stop for questions and stop talking at you. All right, yes.
I was curious about the first tool that we presented, the brain effect. Can you use it for structural MRI or like something that's not functional?
So at the moment, we've only developed it for functional stuff, but it could, if you contributed structural data in the format that we specified, it would be very easy to run the tests. Well, someone would have to actually do it, but it's just kind of a click. It will assume the test structure and we could just run it through the pipeline. But we currently only have fMRI data, but you could contribute structural, you could contribute EEG, FNIRS. We're just asking for larger data sets. Yeah, thank you. Just gonna look at questions online. Oh yes, JD.
On the visualization and the tools, I think like a lot of the GUI aspect is often up to reproduce and to like you have like ways of like pushing the scripts what has been decided on the GUI. Also, but do you think the evolution of those tools are going to happen like there's a new version of something like they're behind the scene components that are quite independent, like containers and things that can be replaced, or is it inspiration?
Yeah, that's super important. So we had really, really great feedback from a reviewer to help encourage us to create some regression tests for brain effects, for example. And the way that we're thinking about it philosophically right now is to take kind of an image and just have recorded the values of everything in that image and have that as like our main reference that we're going to work with. And then compare any new version that creates an image to that original image. And ideally, what you would do is each subsequent version, like you could compare pairwise to each, like this version gets compared to the previous version. But right now we're thinking of like, if we have one version that we consider to be our like release version and everything else is development, then we would compare it to that. But I think it would be also a good idea to record everything about this system state. I think that's what Xenios had been working on in BISWeb. But that's right now, that's kind of my simpler philosophy, is have one thing that we think works really well and let that be our reference. But I'm also really interested in hearing anyone else's thoughts if they have other opinions about that. Thank you. Yeah.
I asked this last year. Still getting update, but
Yeah.
I'm still waiting for the parallel notes. And so I'm wondering if we just talk a little about the experience of getting it to work.
Yeah, so that's a question. Oh, yes. So the experience of getting different languages to work with WebAssembly. Yeah, so I will say very honestly, this is kind of that part of managing the compilation is really Xenios's and Dustin's thing. So I will really have to point you in their direction. I kind of did some development of some smaller encapsulated pieces. So unfortunately, yeah, but fortunately, because they're awesome and they love to talk to people about this sort of thing. So if you're interested, we should really put you in touch.
Yeah, totally. Maybe I can ask.
Yeah.
is your sense that, it's feasible for neuroscience tools?
Oh, yes, yes, definitely. So we already have a number of different tools like the ones we talked about with the smoothing and the registration algorithms that if they're written in C++ or R, we have already integrated into BISWeb. And we were working sort of a playful semi-hackathon project that I was just kind of curious about with Rob, with Bob Cox, trying to get some of the statistical algorithms in there. And we had both between him and Xenios and me just sort of playing around and trying to help out with some stuff. We had a proof of concept little piece of AFNI that we did have running, actually another smoothing algorithm in BISWeb. But some of the older, like really important softwares that we use, it can be sometimes hard to extract kind of the functional pieces that you need and then just plug them in. So I think that's the harder part, is taking the existing software and pulling out and encapsulating the pieces that we need to specifically plug in. But if you have, your own C++ algorithm or your own R script, it can be done.
We had someone just had their hand up on Zoom. If
Great.
that person still wants to ask a question.
Oh,
Hi, yeah, that was me. This is a question, it's not mostly related, it's not the most closely related to this talk, but I was hoping to ask about the retest reliability stuff of neuroimaging data. I feel like my research group and many others have found that even like within individuals in like longitudinal scans, reliability of functional activation and connectivity data is remarkably low. So just like given your work on this topic, I was wondering how you're thinking about this issue. Could we still make inferences from like ROI analyses, or like are there specific strategies that are helpful?
thank you. This is a great question. And it's also nice because it lets me talk about two things at once, the reliability part and the validity part. And we see, effect sizes are really low at the edge level or the voxel level. Reliability is also very low at the edge level or the voxel level. But when you look at things like discriminability or fingerprinting, which are multivariate measures of reliability, or if you look at, multivariate inferential techniques, like I was saying, the canonical correlation or Hotelling t-squared, we tend to see much bigger effect sizes and much better reliability. Like we can distinguish people pretty well with, let's say, 15 minutes of data using fingerprinting or using discriminability. So kind of my message there is when we focus, which we historically do in neuroimaging, at these very univariate levels of inference, we tend to not be very well powered and we tend to not have very reliable estimates. But we can get pretty good power and reliability when we zoom out and use larger scale network level or multivariate estimates. I think multivariate stuff it can be a little bit scary to people because you lose the ability to do this very spatially specific inference. There are some ways you could think about like looking at the multivariate effect and seeing, just decompose all the different dimensions of the effect. Or you could use network level stuff, which is more spatially specific. And it reflects the truth. We tend to see things are grouped together within networks. So that is when people kind of talk about the worry about low reliability or, low power, although, that's a conversation that's still ongoing. We don't necessarily talk as much about that. That's kind of what I usually respond with. We should start with sort of multivariate, larger scale techniques, especially for smaller end studies. Thank you, Michelle.
Thanks.
And one more.
Yeah.
So I feel like there's often a lot of tension in science, especially for students and postdocs. The two working on your analysis or paper, whatever, working on interface with a tool or something like that can. I wonder if you comment a little about how you do best for students.
That's another excellent question. Yeah. Oh, yes, thank you. I definitely should. We're talking about how students can budget their time between the two extremes of, working on a specific, more, let's say, outcome-oriented project, or let's say examining some psychological phenomenon versus, working on a specific tool or method. And I think it's such a good question because, methods, I think support for methods development is increasing and appreciation for methods development is really increasing in neuroimaging. So there are a lot of people who care about that, especially people who are in the open science community. So you can, build a career on doing some methods development, but at the same time, it's very hard. Historically, it has been harder to get funding for some methods development stuff than for more kind of applied stuff. I think it's kind of changing now, but the way I often think about when I'm training people or working with people these days is it's helpful to have one project that's very safe and you're going to publish it and it will, I don't know, it'll be appreciated. And then another project or so that's kind of risky. But maybe I would add that it's helpful to be involved in communities like this or in hackathons and stuff where you're kind of selfishly getting a lot of methods experience, like you're getting a lot of really critical training that will make you a better researcher, even if you don't want to be a methodologist, but you also get a taste of some methods development. And a lot of people in our field who started off really interested in applied questions, including me, end up going in the direction of methodology development because they realize they can't actually answer the questions in a robust way without better methods. So I think it's a lot of people are also appreciating that. So there's a lot of excitement about it. So I wouldn't be too scared to go off of it, but it is a thing that's sort of changing. So it makes sense to always kind of hedge your bets and try a couple of different things. I think I saw a hand up here. Maybe not. Maybe it was a stretch. David, yeah.
Thank you. Some of the papers that are most cited are the method papers or toolbox papers because you do that and you do some of the methods work is actually super well. The paper is one will
Yeah, you're absolutely right. Some of our critical tools are some of the most cited papers out there. So there's definitely a possibility to build a career on it. There are aspects of our ecosystem that can push against it in some ways, but there are definitely really great cases that are successful. And yeah, like some of the papers that you can think about that people are talking about the most in the past decade or so are papers that question methods. Any other questions, guys? I think it's time to wrap up.
Thank you.
Thank you, guys.